10 mils of 1 molar HCl, that's going to contain 0.01 moles of H+. So when I dump that into the water, I'm going to end up with 1 litre of solution. 990 plus 10 is 1 litre. And because I've got 0.01 moles per litre of H+, that means the pH is going to be 2. So what's happened, upon addition of 10 mils of 1 molar HCl, the pH has dropped from 7 to 2. That's 5 pH units. Now if I replace this water with a buffer solution, buffer is a solution of a weak acid and its conjugate base, and what's going to happen is I'm going to add 10 mils of 1 molar HCl. The pH of the buffer might be 4.7. After I add this, the pH might only go down to 4.5. The reason it's going to go down a little bit is because we're adding acid, which is going to decrease the pH. But because we're using a buffer solution, the pH is going to decrease only slightly. Alright, let's look at something else here. And this is I'm going to try and explain why a buffer solution does result in only small changes in pH when a strong acid or a strong base is added to the buffer solution. So here's our buffer solution. We're going to have a mixture of a weak acid, which I'm calling AH, and its conjugate base, which I'm calling A-. So I've got 4 AHs and 4 A-. Usually buffers are pretty much equal mixtures of the two. Now if I add 1 H+, and this is 1 H+ from a strong acid, then what's going to happen is that the A-, or one of the A-, just one, is going to react with the 1 H+ we added, and it's going to become AH. So in the solution we're going to have 1, 2, 3, 4, 5 AHs now, and 3 A-. Now this is only going to result in a minimal decrease in pH, because all we've done is just increased the amount of a weak acid a little bit more and decreased the amount of a weak conjugate base. This has nowhere near the effect of adding a strong acid to the solution. So just increasing the concentration of a weak acid is not going to really affect the pH very much. Now this is a situation where we've got the original buffer solution again, 4 AHs, 4 A-. Now I'm going to add OH-, and this is a strong base to the buffer solution. So one acid molecule, just one of the AHs, will react with the OH-, and we'll get A-. I'll complete that reaction. We'll get A- plus H2O as well. The H2O doesn't matter so much, but the point being here that the OH- has reacted with the AH, and we've gotten just one more molecule of A-. And again, this is going to send the pH up a little bit because it's going to be a little bit more basic, but it's not going to be basic by a huge amount. What you must remember with buffers is that once a strong acid or a strong base is added to the buffer solution, it's gone. It doesn't exist anymore because it's reacted with the components of the buffer, either the acid or the basic component, and it no longer exists. And if it no longer exists, it cannot drop the pH like we saw in this one over here, where we saw the pH drop like a stone when we added the concentrated hydrochloric acid. There was nothing in here to eat the hydrochloric acid up. In the buffer solution, we've got something to get rid of the H+ that's in this solution. So the only thing we're going to be left with is just increases, small increases in the amount of weak acid or weak base in the solution. So that's why buffers are so effective at resisting changes in pH.